Okay, let's dive in. The topic today, it takes us into a pretty specific and I think really intriguing area. We're talking about applying mathematics, specifically differentiation, to understand something vital happening in nature.
Right. And based on the material, we're focusing squarely on differentiation in forest resources technology,
Where?
specifically looking at the rate of carbon sequestration in forests. So if you're studying mathematics right now, maybe hitting that chapter on differentiation and integration, this is directly relevant.
Exactly. So our mission here really is to unpack that connection for you. We want to show how these, sometimes abstract concepts you're learning in calculus,
Yeah.
how they can actually be used to tackle a big real-world environmental question,
Right.
which is how quickly are forests actually absorbing carbon, pulling it out of the atmosphere.
Yeah, and when you're learning differentiation, it's all about measuring that instantaneous rate of change, right? Like how fast something is changing at one specific moment.
Exactly.
And that idea, rate of change, well, that's completely central when we talk about carbon sequestration. It's not static.
No, not at all. Forests aren't just like sitting there holding carbon. They're dynamic. They're actively taking it in, storing it over time. It's a process, and it happens at a certain speed, a rate.
Right. Think about, say, just one tree. It grows, it adds mass, right?
Hmm.
And a lot of that mass is carbon it pulled from the air. Photosynthesis. So how fast is it adding that carbon this year? Does that speed change as the tree gets older?
And then you scale that up. Think about a whole forest stand. How quickly is that entire ecosystem adding to its carbon stock? How quickly that speed of accumulation, that's the rate of carbon sequestration.
And this is precisely where differentiation becomes, well, essential. It's the tool you need. If you can model the total carbon stored in a forest over time with a function, let's call it CT, C for carbon, T for time,
Okay, CT.
then the derivative of that function, C prime of T or
That's
CT,
right.
that tells you exactly the rate, the speed at which carbon is being stored at any given moment, T.
And this isn't just some abstract math exercise. Understanding this rate, the CT, is super important in fields like forest resources technology.
Absolutely. That whole field is about managing forests sustainably for timber, conservation, climate, you name it.
Yeah.
And to manage them well, especially for climate benefits, you have to be able to quantify these processes. Knowing the rate lets people make much smarter decisions.
Right. Because knowing the rate, CT, gives you more than just knowing the total amount stored, CT. It tells you about the dynamics. It helps predict maybe future sequestration under different conditions.
Precisely. Or different management styles. It lets researchers figure out, say, the age at which a certain type of forest is soaking up carbon most efficiently, finding that peak rate.
Ah, that peak rate idea is interesting because it wouldn't be constant, would it?
Not at all. You might have young forests growing really fast, but maybe their total carbon stored is still relatively low. Then you get mature forests holding huge amounts of carbon, but maybe the rate of adding new carbon has started to slow down a bit.
Because growth slows down naturally.
Yeah. So knowing the derivative C lets us pinpoint when that peak efficiency happens, or maybe how the rate changes if the forest is stressed, drought, disease, that kind of thing.
And getting that initial function, CT, the one you differentiate, that takes a lot of real-world work, right?
Oh, definitely. That means measuring trees, biomass, soil carbon, sometimes over decades,
Yeah.
across all sorts of different forests. And the models, the functions themselves, they aren't usually simple. They try to capture age, species, density, weather. It gets complex.
So differentiating those complex models gives you that really nuanced understanding of the rate that, say, a forest manager needs.
Exactly. It provides that dynamic picture.
So when you're working through derivatives in class, you can sort of picture CT as all the carbon locked up in a forest, and CT as the actual speed, the pulse of carbon being drawn down from the atmosphere and stored away year by year, even day by day.
Yeah, it really bridges that gap, doesn't it, between the curves on a graph and a vital process happening out there in the world.
It makes the math feel very tangible.
Well, if we step back and look at the bigger picture here, what's really, I think, powerful is seeing how this mathematical tool, differentiation, designed purely to measure rate of change, is exactly the right tool to quantify something as, well, as biological and dynamic as carbon uptake in forests. It just highlights how math can illuminate these complex natural systems.
It really does, and maybe that leaves you, the listener, with something to think about. As you continue with your studies, consider what other environmental processes out there involve a crucial rate of change. Things like, I don't know, population growth, or maybe how quickly pollutants spread in water, even the speed of glacier melt. Could these also be better understood using that mathematical lens you're developing? Something to mull over.